All right, welcome to our channel. In this video, we're going to introduce two vector operators defined in terms of the del operator. So the first operator we're going to talk about is the divergence, or the first quantity is actually the divergence of vector. So given a vector f with x component f1, y component f2, and z component f3, then its divergence is defined as the x derivative of the x component, y derivative of the y component, plus the z derivative of the z component. Now, since the dot product is a scalar, so that means the divergence of a quantity is also a scalar. It's just going to give us a number. Geometrically, the divergence of f is a measure that tells us how much a vector f spreads out or diverges from a point in question. So that means, for instance, if we have got a vector field like this, then at this point, the divergence of this vector is clearly going to be non-zero, because if you draw a circle here, then you can see that all the components are going outside. So, and then the opposite, of course, is a vector field for a sink, which is going to be like this. So this one at that point, it's going to have a negative divergence, because instead of spreading out, the components are coming in. And then on the other hand, if you've got something like this uniform flow, then this vector field is going to have divergence 0, because if you choose any point, then the amount of components going in is going to be equal to the amount of components going out. For instance, here, this side things are going in, and that side things are going out. Okay, then if a vector field is such that its divergence is 0, then that vector field is called solenoidal. So that is in terms of the divergence. Then the other quantity is the curl of a vector. So the curl of a vector f is defined as the cross product, well, if you like, so it's del cross f, where del is the operator that we introduced a bit earlier. So this is the operator del, that's j here, and then actually we can, because this is an operator, can bring these in front. So I, j, and then k, that's the z component. So here, for instance, we're using the shortened form of partial x. So these are the partial derivatives of x, y, and z respectively, and then these are the quantities, the components of f, that's the x and the y and the z. Then geometrically, the curl of f is a measure of how much f curls around a point in question. So in this case, if we take a point like this, if our vector is something like that, then the curl of this vector is going to be non-zero, because you can see that the components or the streamlines of these are curling around. Okay, and then if the curl of or the other thing to note, of course, is that the curl of a vector is going to be a vector itself. It's going to have 3 components. Now, if the curl of the vector is 0, then that vector is called irrotational. Okay, so lastly in this video, we're just going to introduce some vector operators which are defined in terms of the del operator. These are not going to be it's not going to be a full list of them. We're just going to introduce about 9 or 10, and then from these, if you come across others, of course, we hope that you can understand how the principles follow. All right, so if f and g are differentiable vector fields, vector field here is the same as vector function, while phi and psi are differentiable scalar fields. Again here we can use scalar functions. Then we've got these properties. So the grad of phi plus psi is equal to the grad of phi plus the grad of phi. And then the divergence of f plus g is the divergence of f plus the divergence of g. Similarly, for the curl, then here there's the divergence of phi times f. So remember, phi is a scalar, so this is going to be given by the sum of these two quantities. We're going to prove this one in a moment below. And then this is a similar property about the curl of phi times f. And then this one is the divergence of grad phi. Remember, phi is a scalar, so this one is equal to the del squared of phi. Del squared is called the Laplacian operator. So this is the Laplacian of phi. In terms of if we write it out, this is going to be the second order derivative of phi with respect to x plus the second order derivative of phi with respect to y plus the second order derivative of phi with respect to z. So that's what this quantity is equal there. Then property number 7 is talking about the curl of grad, and this one is equal to 0, so it's obviously going to be a vector because it's a vector, and then you're taking the curl of that. This one, on the other hand, is going to be scalar because you've got a vector here, and then you take the divergence of that. We say divergence is always a scalar because that's a dot product, and this is the last one. Okay, so we are going to prove property number 4 and property number 7, and then we're going to give you to have a go at proving property number 8. So there is property number 4. So let's just see if we can just copy it. And then see if we can prove it there. Right. So this is saying that the divergence, surely this didn't work well. Let's try it again. So there is property number 4. There we go. Okay. And then, yeah. So the left hand side is the divergence of phi times f. Now, so remember, f is equal to f1, f2, f3. So these are scalar functions. So phi times f, where phi is a scalar, it's going to be phi times f1, and then phi times f2, phi times f3. Then the divergence of this, so divergence of that, so it's just going to be the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. And then using the product rule, for this one we're going to get two terms. So the first term, for instance, is going to be phi times the x derivative of this, and then the second term is going to be the x derivative of phi times f1. Then similarly for the second term, this is what we're going to have, and then phi here with respect to y. And then for the third term, it's going to be phi the z derivative of f3 plus the derivative of phi with respect to z times f3. Now, if we collect terms, so if we want to bring these terms together and these terms together, so what this is going to give us is the following. So we can factor out phi from this group of terms. Then we're going to have partial f1 partial x plus partial f2 partial y plus partial f3 partial z. And then from these terms, okay, maybe just for now, let's just write them out as they are. So this is partial phi, partial x f1, partial phi, partial y f2, partial phi, partial z f3. Now this term here, you will recognize it as just the divergence of f. So that means we can write that first term as phi into the divergence of f. That's this term here. And then this one here, we can write it as the dot product of phi x, phi y, phi z dot f1, f2, f3. So this is just f, and this one is grad phi. So that means we are going to have a divergence of f plus grad phi dot f. Okay, and this is actually the right hand side of the formula we are trying to prove. Okay, so here is the first term that we have below, and here is the second term. We've got grad phi dot f. So that's the proof for property number 4. We're now going to have a go at proving property number 7, and then we'll give you property number 8 to have a go at proving. Okay, so for property number 8, so rather property number 7, okay, so it says the curl of grad phi is the 0 vector. So let's start with grad phi. Grad phi is simply the x derivative of phi, and then the y component is going to be the y derivative of phi, and that's going to be, the third one is the z component. Alternatively, we can write this like this using the subscript notation of the partial derivative. Okay, then the curl of this, as we are going to want to work out. So the curl of quad phi is going to be this 3 by 3 determinant x, y, z derivative. We're going to have phi x here, phi y here, phi z. So this is going to be the x component we're going to get by doing this the determinant of that. So it's going to be the y derivative of this. So it's going to be phi yz, and then this one is going to be the z derivative. So that is going to be zy. And then for the j component, it's going to be phi xz minus phi zx, and then finally for the j component, it's going to be these ones here. So it's going to be phi xy minus phi yx. Now remember, we assumed that phi is a differentiable function. So for all differentiable functions, the mixed derivatives are equal. What does this mean? This means that the second order derivative of phi with respect to x, then with respect to y, is always going to be equal to the second order derivative of phi with respect to y, and then with respect to x. So that means this term is going to be 0, this term is going to be 0, and that term is going to be 0. And so we have got the 0 vector, which brings to the end our proof for property number 7. We're going to give you a few minutes. So we just advise that you pause the video, then have a go at property number 8, and then when you continue the video, you can compare with our solution. All right, we're now going to scroll down to our proof for property number 8. So we hope that you've had a go. So the first thing we do is to work out the curl of f, where we're assuming that f is general with f1, f2, f3 as the x, y, z components. So that is going to give us this vector here. Then when we take the divergence of that, so divergence does the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. And then removing these brackets here, this one, for instance, is going to be the second order derivative of f3 with respect to x and y. This one, second order derivative of f2 with respect to x and z. And then similarly for the other 4 terms. Now if you look at the terms involving f3, you've got this one here, xy, f3, xy, this one is yz. Just one moment, looks like there is an error here. So the first one is f3, yeah, so this is xy, and then this is xz, xy here, f3, f2, xz. Okay, okay, maybe let's go to the f2 one. There's f2 xz. Oh, looks like there's some errors here. Okay, let's go through this carefully. xy, xz, xz, yz, yz, yx, y. This is supposed to be x. Okay, then zx, z. This is supposed to be x. Then finally z and y. zy. All right, so f3xy here, f3yx, and as we already mentioned, if f3 is differentiable, the mixed derivatives will be equal. Then f2xz here, where is the other f2 here? Zx, this one is minus, this one is plus, and then these two. So this gives us the zero scalar. All right, thank you.